Thanks very much for the opportunity to speak at this workshop. I'd like to talk about robot hand-eye coordination, and the work that I'm going to present is the work of my postdocs, Yuxi Leitner, and my former students, Fangyi Zhang, Doug Morrison, Jesse Haviland, and Ben Burgess-Limerick. If we look objectively at what computers and robots can do, we know for certain tasks they're awesome. For example, in sort of classical board games, classical hard AI problems, they're way better than human beings at the game of chess, and more recently at the game of Go. But when it comes to tasks like hand-eye coordination, manipulation of objects, as shown here, actually robots are way inferior to very small children. And even if we could create a robot system to do this particular job of picking up these wooden chess pieces, if we then showed it different kinds of chess pieces, it's very likely that it would be confounded. It wouldn't have the ability to generalize, and that weakness is particularly apparent in its visual perception system. So if you can look at the capabilities of modern robots, you look at the capabilities of robot manipulator arms that are widely used in manufacturing, or you look at the new class of mobile robots that are used in logistics, they're very, very capable. The arm robot manipulators are fast, accurate, and strong, and companies like Amazon have built up massive fleets with hundreds of thousands of robots that power their business. Yet despite the wonderful capabilities of these robots, we still see very low uptake of robots and automation technologies in many industries. So small batch manufacturing, particularly agriculture, which you could think of as food manufacturing, mining, building and construction, which you could think of as building manufacturing, and also tasks like hospital logistics. So you have to ask the question why, when robotics is a 60-year-old technology, are there so few robots in the world? There are perhaps a few million robots doing manufacturing, there may be a few tens of millions of robot vacuum cleaners, but in many areas of our economy that are particularly important, we're not seeing very many robots at all. So I would argue that what's missing is the ability of robots to perform hand-eye coordination. It's something humans can do wonderfully well in all sorts of different tasks that we turn our minds to. So here are some very extreme examples. So the young girl on the left is solving a Rubik's Cube. So she is looking at the cube with her eyes. She's building up a mental model of the cube, reasoning about how to solve it, and then using her hands to manipulate the cube to the desired end goal. The driving example here, the human driver is perceiving the world through their eyes, and really then they're actuating the car through their hands and their feet. And so really this is a closed loop system, and a critical part of that closed loop system is a human performing hand-eye coordination. And down in the bottom right, you see some examples of human beings doing juggling. This is very, very dynamic activity. And so they're using their eyes to assess not just where the objects are right now, at this point in time, but where the objects will be into the future. It's a critically important part of doing these dynamic activities successfully. And it's something that our visual system is actually very, very good at predicting where things will be in the future. And I'd argue that that has a huge survival advantage to know not just where the tiger is, but where the tiger will be in the near-term future. And that's very important for survival of all animals. Another thing I like to talk about as kind of a pet peeve of mine is that we routinely solve problems, humans routinely solve problems like this without any knowledge of the pose of the objects involved. So most of us can thread a needle, put a very fine piece of cotton through a fairly small hole in a needle, and we do that without estimating the pose of the needle or the piece of cotton. But if you gave this problem to a roboticist, the first thing they would probably try and do is to estimate the pose of these things and then come up with an algorithm that moves the end of the cotton to the pose of the hole in the needle and therefore solve the problem. It's a complex way to solve it, and I'd argue that it's not particularly robust. The way that humans do it is actually more robust, and I'll come back to that in a moment. So So a key aspect of hand-eye coordination is clearly the eye. And the eye is a biological technology. It was invented about 540 million years ago. So it's relatively late, actually, in terms of life on planet Earth. But when vision appeared on this planet, uh, evolution took big step forward. So it led to a huge explosion in the species on the planet, something that we refer to as the Cambrian explosion. There's an interesting theory called the light switch theory, which suggests that the arrival of visual capability in organisms led to essentially an arms race between predators and prey that drove the rapid evolution, exploration with different forms and features of creatures, leading to the richness that we see in the world today. And eyes today are everywhere. Not all creatures have eyes like our own two eyes. There are creatures with many, many eyes, and eyes formed on quite different principles. Our eyes are based on lenses, but some sea creatures have eyes that are based on reflective optics, not refractive optics. There's probably 10 different eye designs on the planet at the moment, and 96% of all species have eyes. So eyes are the secret sauce really for doing hand-eye coordination. The other critically important part of hand-eye coordination is the brain, right? That's what processes the visual information. For ourselves, we've probably got a pair of 100 megapixel cameras in the front of our head, and we have a large brain, 1,500 grams of grey matter, 10 to the 11 neurons. About a third of that is dedicated to visual processing. But even very small and simple creatures like insects, bee shown here has got a brain that weighs just a gram, yet you can see it performing a very complex body-flower coordination problem. So awesome skill with really very, very small computational resources deployed. So if we look at the traditional way that a roboticist might tackle this is that we would have a control system sensors that tell us where the joints of a robot are, and we perform forward kinematics, inverse kinematics to drive the end effector of the robot to a desired point in the world, or desired pose within the world. The robot doesn't actually know where its end effector is, it's inferred from joint sensor measurements. The robot also doesn't know where the object that it's working on is, so it can't do hand-eye coordination. It can't move its hand to minimize the distance between the hand and the object that it's working with. It's all done by inference. A manufacturing engineer is very good at arranging the working environment of a robot manipulator arm so that it can perform useful tasks even if it can't actually see where the objects it's working with are. It's all done by relying on absolute precision. Again, that's in contrast with the way human beings solve tasks by hand-eye coordination, moving our fingers so that the piece of cotton moves through the hole in the needle. Now in robotics, this is a problem that has been tackled, and if you look at the top right, there are 4 faint crosses, and what you'll see is the robot is moving the camera so that the centers of the dots become aligned with the crosses. And this is a technique that we call visual servoing, and I'll just repeat that video so you can see it again. So what this robot is doing is actually moving its camera to make the image into a desired state. And this is what we do. This is an example really of hand-eye coordination. And that last example was rather slow, but if you take account of the dynamics and the latency in the system, then you can actually perform quite high performance visual servoing. And this is some work that I did a long, long time ago, showing a robot with a camera actually tracking on the right hand side an object that's falling under the influence of gravity, and on the left hand side it's tracking an object moving with quite significant acceleration profile on a turntable. And so we can do a task like the needle threading task on a much larger scale. So this is some work I did when I was at CSRO. And we have a forklift truck with a hook. And we use cameras to guide the forklift truck so that it can put the hook through the handle on this large crucible and pick it up and move it around. And here's a trial we did over the course of a whole day where we just picked the crucible up, moved it to a random location, dropped it, picked it up, and moved it to another random location. We did this over and over again to give some idea of the reliability of this approach, which does not rely at all on the absolute pose of the vehicle or the absolute pose of the crucible. It's all done by relative positioning. And you can see in this case we cheated. We put some barcodes on the crucible, but I think today we have vision techniques that would allow us to do it without using codes like that. So we got interested a few years ago in the task of picking things up, and particularly motivated by this problem from logistics where fleets of robots move these shelf units around a fulfillment center, but we need a human being at the end to take the items out of the shelf units and put them into the packing boxes which go to the customers. And that's really because humans have got the required level of hand-eye coordination to do this complex task of taking the objects out of the shelves. So Amazon pitched this problem as a competition, and our lab entered for the first time in 2016, and that was probably the second or third year of the competition. And our first entry was a Baxter robot with a not particularly well-engineered vacuum gripper that reached into the shelf units and attempted to grab the items. It was problematic for all sorts of reasons. It was a great learning experience. We came sixth in the competition, but there were many things that we learnt. We took those forward to the next year of the competition, where it was then called the Amazon Robotics Challenge. And this is the robot that we created. It's a Cartesian manipulator, and the problem had morphed somewhat, so we could actually now pick vertically out of tubs rather than trying to pick horizontally out of the shelf unit that I showed a moment ago. So the Cartesian robot that we created is interesting. It was largely 3D printed, had only 3 degrees of freedom. It had 2 grippers. And so we learned that suction grippers are very, very versatile. They can pick up a lot of objects, but there are some problematic objects in the Amazon challenge which cannot be picked up with a suction gripper. And so we ended up with a robot with 2 grippers, a standard 2-finger pinch gripper and a suction gripper. In his video showing the robot at work, and here you can see it's got its 2-finger gripper downward. It's reaching into the bin and picking up a soft object. It's going to pick that up and drop it into one of the output totes. You see the robot now is going to rotate its hand around to deploy the vacuum gripper, which is going to come down and pick up this plastic bag of socks and put that into the output tote as well. So another part of the secret sauce, I think, for this particular robot was a pretty advanced vision system developed by colleagues within the Australian Centre for Robotic Vision, and it was called RefineNet, and took an RGBD image and was able to classify and locate the objects even if they overlapped. So on the left-hand side you can see the RGB image, on the right-hand side you can see the outlines of the objects and the labels and the confidence that we have in those particular labels. So the combination of the robot and of the RefineNet gave us an approach that worked very, very well. We won the competition in 2017, which we're pretty happy about. And that then led really to 2 different developments within our lab. The first development actually was a spin-out. So one of my postdocs, Yuxi Leitner, took the technology that was developed for the Amazon Challenge out in a company called Lyro. And Lyro's focus really is on picking and packing uneven sized objects, uneven sized and shaped objects, particularly natural products or fruit. And so they've been able to demonstrate wonderful results in terms of picking and packing these products. And at this point, I should declare that I have an interest. I am an advisor to Lyra Robotics. Here's a video of the Lyra robot picking grapefruits and putting them into a packing container. So this is a task that's done not in factories but in packing sheds on farms, and it's one where at the moment there's very, very little automation deployed. And certainly in Australia we have significant problems with getting labour in these rural areas, and that's massively exacerbated by COVID. The other development within our lab was to start looking at reinforcement learning as a way of tackling problems like grasping. And if you're not familiar with reinforcement learning, this animation I think shows it very well. It's essentially trial and error. So this robot is trying to learn to walk, and each attempt to walk is scored, and over time it will learn to walk better and better. So if I fast forward a bit, you can see at this point, episode 4800, it's doing well until that point. And I move up a bit further, we can see it's now starting to walk with some sort of somewhat strange gaits and still falls over. But when you get up here to over 6,000 learning episodes, it's doing quite a reasonable job of walking. So one of my students, Fangi Zhang, was interested in applying reinforcement learning, and this is back 2014, 2015. And so we developed a fairly realistic vision-based simulator. We had a Baxter robot in there, and we were using one of Baxter's hand cameras to look at the scene, Baxter's other hand with a vacuum gripper to reach towards a blue cube. We wanted to teach the robot to be able to reach to the blue cube in the presence of clutter. So there's a lot of other objects there to confound it. So we were able to teach the skill to the robot in simulation. The challenging part is always crossing what's called the simulation to real gap. And that's how do we get the skill learnt in simulation to work in the real world. When the camera properties are going to be slightly different, the camera is not going to be placed at exactly the same location as it is in simulation. Lighting conditions will be different. There's more realistic texture. There are shadows and reflections and all these sorts of things. So Fangi's PhD work was really concerned with how do we minimize the amount of tweaking, the amount of extra label data that we need in order to perform this task, learned in simulation, but perform it in the real world. So we came up with a modular neural network architecture. The big piece on the left is the perception stack. It comes down through a bottleneck and then goes into a fully connected network which outputs joint velocities. So convolutional neural network on the left and fully connected network on the right. This network takes in an RGB image and outputs a set of joint velocities. So there's no inverse kinematics in here, there is no planner, there's no PID control loop. It's image in, joint velocities out, and then we send those straight to the Baxter robot. So here it is running. You can see the hand camera up in the air at the back, and you see the other hand which is relentlessly reaching for the blue cube. And Fangi's moving it around, changing the configuration of the clutter. The robot is really quite relentless. Now I have to say that that's all this robot can do, or all this controller can do, is reach towards a blue cube. So it has only a single skill. But I think it's fascinating what we can do with reinforcement learning with a network that takes an image and outputs velocities directly to the robot's joints. Another area of research that kicked off after the Amazon challenge was looking at grasping. So what I showed you before was reaching, it's moving toward the object. Next bit is how do we actually pick it up? And the traditional approach is you take a depth image of the object, you propose a number of sample grasps, you rank them, you choose one, and now it's often quite time consuming, might take a second or more, and then you execute the chosen grasp, generally open loop. And that implies then that your object has to be stationary. So my student Doug Morrison looked at this and he came up with a generative neural network that takes a depth image and outputs 3 images. One is a grasp quality map, one's a grasp width map, and one is a grasp angle map. and I'll show those here. So the depth image leads to these three output images, and the grass quality image is essentially a heat map. So where it's darkest indicates the points in the image where the best graphs are to be found. And if we look up the corresponding pixel locations in the grasp width image, that tells us how far apart our fingers should be to execute that grasp. We look up the corresponding pixel in the grasp angle image, and that tells us the orientation of our fingers required to execute the grasp. So we look at the output images, we choose the best grasp quality, and then we look up the width and the angle, and we get the robot to do that. Now this network gives us these images at a rate of about 30 Hertz, so we can do it while we're reaching toward the object. And once again, it is a deep neural network. It's trained from a number of standard grasping data sets. And here you can see it working. You can see the object moving around. The dot indicates the point of highest grasp quality, and the coordinate frame on the very rightmost image here is indicating the position and orientation of the fingers to achieve that best possible grasp. And here you can see it's reaching towards an object that's moving, sliding down and grabbing it. And another example of the robot reaching amongst clutter. So the robot isn't being programmed to pick up the banana, it's really being programmed to find the most graspable object in the scene and pick it up. Now, one of the challenges with this work is that the RGBT sensor that we have on the end of the robot has got a limited working range. And you'll notice in all these examples, we stop moving the objects some time before the robot comes down for the final piece of the grasp, right? And the reason for that is that the RGBT sensors have got a minimum sensing distance. It's about 16 centimeters. And so if the camera is closer than 16 centimeters, there is no grasp, no depth image available, and therefore we can't synthesize a grasp. So we have to stop moving the objects before the robot is closer than 16 centimeters. So it's kind of a serious limitation. So that got us thinking then about the problem of where should we put the cameras. And traditionally the cameras have been either placed on the wrist or they're being placed at a fixed location within the scene. But if the object's got clutter, then neither of these locations are particularly optimal. And these renders here show some examples of what the scene looks like from a fixed camera view or from a wrist camera view in the presence of clutter. And it occurred to us that the problem of grasping, like the problem of threading a needle, is all about where are the fingers relative to the object that we're trying to pick up. And so we call this the last inch problem, and we figured the best place to put the cameras is really close to the fingers, looking at the fingers and the objects themselves. So we've come up with this two camera configuration shown here with overlapping fields of view. And this is the work of my student Ben Burgess-Limerick. Now you might say that rapidly moving objects is not a very realistic problem, but in a lot of manufacturing situations we do have objects that are moving. On conveyor belts, the objects move in a very predictable way, but fruit rolling around on a belt moves in a very unpredictable way. And if your robot arm was mounted on a moving platform, for instance, an underwater robot or a free-floating robot on a space station, then we have the base of the arm moving around, and it's the same problem, really, as the objects moving around and the base of the arm being fixed. So we think this is a problem that has actually got some quite general applications. So to investigate the performance of robot grasping algorithms in the presence of dynamic objects, we built a low-cost testbed that's easy to reproduce. We've come up with a number of standard trajectories for the table that holds the object, and here I'll show you some examples of this in action. So the rig in the foreground is the platform, which is driven by two motors, so it moves in the X and Y direction, doesn't rotate. And now what you're going to see is the robot moving, and it lost track of the object. The object suddenly moved backwards, and with a single camera view, it went out of the view of the wrist camera, and the grasp was unsuccessful. Whereas if I run the grasper using the two hand-based cameras, it almost always has the object in its field of view and the grasp is more successful. So if we do trials over a large number of grasps, it's very, very clear that the dual hand camera approach is much, much more reliable than the wrist camera approach. And this is a simple case with just dynamic motion of the object and doesn't include any clutter. The final piece of work that I'd like to talk about is a test bed, and this is work done by my PhD student Jesse Haviland, of combining some of these technologies into a mobile manipulation platform. And what we see here is fairly graceful and seamless motion of mobile base and an arm working in harmony using the grasping technique that I showed earlier, and it's just moving objects from one tote to another. The control of the arm and the base is done by a single control framework. It's framed as a quadratic program. The arm is maintained in a pose of maximum dexterity, far away from joint limits. It avoids collisions with objects, and it has the ability to detect when it's failed, and it will retry. What I like about this work is that it's done largely using reactive control, and it's very, very graceful. There are no long pauses for motion planning, and the motion you see of the base, the way it does its reversing as it's moving from one tote to the other, is not pre-programmed. There's no trajectory generator there. That's an emergent behavior of the control law that we've programmed. Final application I'd like to talk about is in fruit picking. And this is with fruit that's still on the bush, and here we're picking capsicums or red peppers. We have an RGBD sensor on the end of a UR5 robot. On the left-hand side, you see colored point cloud that we put together by moving the camera to a number of different viewpoints. We can fit a shape to it, we can find its pose, move towards it with a vacuum gripper, sever the stalk, and we end up with the fruit hanging in the hand of the robot. We can drop that and then reset. So this has also led to another direction of work, if you like, in greenhouse automation. And what I think will be an important trend in the future is essentially indoor food factories. That these would be city-based facilities packed full of plants and robots that are producing fresh food right where it's needed, rather than having to be transported over large distances from the countryside. So, some take-home thoughts. Hand-eye coordination is a very important skill that's applicable to many tasks. Human beings are awesome at hand-eye coordination, and I think we're proof that a robot with just one or two cameras could be very, very capable. Because if you're very reductionistic about it, we are essentially machines with one or two cameras, big brain, and some fantastic manipulating hands. For robotics, this capability is still quite immature. So the challenge for us as researchers is not just the cameras, it's understanding how to process the data and integrating that into a robust control framework. Thanks very much for your time.